Superconductivity Part 1, a video created by Madhukeswara RS, Assistant Professor of Physics.
The contents shown here are explained in this video. Superconductivity is a phenomenon in which the electrical resistivity of the material suddenly drops to zero at its transition temperature. This phenomenon was first observed in 1911 by Dutch physicist H. Kamerlinghuis. In 1911, Kamerlinghuis found that at 4.2 Kelvin the resistance in a solid mercury wire immersed in liquid helium suddenly vanished. He was awarded the Nobel Prize for Physics in 1913 for his low-temperature research. The resistivity of the superconducting material, unlike normal conductors, drops to zero when it is cooled below its critical temperature using liquid nitrogen or liquid helium. The materials which exhibits this phenomenon are called superconductors. Only few metals and chemical compounds will exhibit this phenomenon. The resistivity of a superconductor decreases with decrease in temperature like in the case of normal conductors, but it suddenly drops to zero value when the temperature of the material reaches its critical temperature. The animation shown here shows how the resistivity changes from finite to zero and also how the material takes transition from a paramagnetic state to a diamagnetic state when the temperature of the superconducting material is reduced below its critical temperature Tc using liquid nitrogen or liquid helium. The temperature at which the substance takes transition from normal conducting state to superconducting state is called critical temperature or transition temperature. It is represented by Tc. It is different for different superconductors. For example, the critical temperature of mercury is 4.22 Kelvin and that of tin is 3.72 Kelvin. The following experimental facts are observed for superconductors. Effect of impurity. When impurity is added to a superconducting material, it is going to lower its critical temperature without affecting its superconducting property. The transition temperature is usually very sensitive to the presence of magnetic impurities. For example, a few parts per million of manganese in zinc lowers the transition temperature of the zinc considerably. Isotopic effect. It has been observed that the critical temperature of superconductors varies with isotopic mass according to the relation Tcm power beta is equal to constant, where m is the isotopic mass and beta equals 0.5. Example: for isotopes of mercury, Tc varies from 4.185 Kelvin to 4.146 Kelvin. The thermal properties such as the specific heat capacity and thermal conductivity of a superconducting substance changes abruptly when the substance takes transition from normal conducting state to a superconducting state. The variation of specific heat of the electrons of a superconductor with the absolute temperature, T, in the normal and superconducting states is as shown in Figure 1 and 2. Persistent current. The current once set up in a superconducting ring flows indefinitely without any decrement because of its zero resistance property. Such currents are called persistent currents. Effect of magnetic field. When a superconductor is placed in an external magnetic field of strength greater than its critical field value, the material takes transition from a superconducting state to a normal conducting state. Therefore, a magnetic field greater than the critical field value of the given superconducting material is going to spoil its superconducting property. If the external magnetic field to which the superconductor is exposed is sufficiently weak, then the external magnetic fields will not penetrate the superconductor, but remain at its surface. This field expulsion phenomenon is known as the Meissner Effect, after the physicist who first observed it in 1933. That is, the expulsion of a magnetic field from the interior of a superconducting material as the material undergoes transition to the superconducting phase is known as Meissner Effect. Hence, a superconductor in the superconducting state behaves like a diamagnetic material with negative susceptibility. This photo shows a magnetic levitation based on Meissner effect, that is a magnet levitating above a high-temperature superconductor cooled with liquid nitrogen. The minimum magnetic field required to just switch a material from the superconducting state to normal conducting state is called the critical magnetic field. It is denoted by Hc. When the applied magnetic field exceeds the critical field of the given superconducting material, the material takes transition from a superconducting state to a normal conducting state. The variation of critical field of a superconductor with temperature below its critical temperature is based on the relation where Hct is the critical field of the superconductor at T Kelvin, Hc0 is the critical field of the superconductor at 0 Kelvin, and Tc is the critical temperature of the superconductor. Figure 3 shows the graphical representation of variation of critical field of a superconductor with temperature below its critical temperature. Hence, the variation of critical field Hct of a superconductor with temperature T below its critical temperature Tc is as per the relation